Okay, sorry about that. I got suddenly called for some work, so I had to stop there. So let's restart chapter 3 then. This is a good starting point for the second podcast, anyways. 3. Reducing greenhouse gas emissions from agriculture. Because land use and agricultural practices are such a big emitter, they are such big emitters of greenhouse gases, they need to be a big part of our solutions to climate change. The most important things we can do to reduce emissions from land use and agriculture include conserving and restoring tropical forests. Tropical forests can sequester carbon and hold it for a long time, and they have a virtuous cycle of local microclimate, soil carbon, symbiotic relations with all the birds, insects, microbes, and so on and so forth. But if you perturb them, deforest them like it's happening in Amazon, it's known that they can actually end up becoming sources of carbon instead of remaining sinks. New methods of animal agriculture. Animal agriculture is a major source of methane, especially from cattle, sheep, and manure piles. New ways of raising cattle and sheep, including new feed additives such as seaweeds that appear to lower methane emissions, and new grazing techniques, which we'll see below here, can help a great deal. New methods of rice cultivation. Rice is a major source of methane if it is done with this flood irrigation, but there are also ways to do it without this flooding, which is done to remove weeds or kill the weeds essentially. But more research in genetic and agronomic improvements to rice cultivation is needed. More prudent use of nitrogen fertilizers and manure farming. This is obviously very tempting for farmers to dump fertilizers, especially in countries where fertilizers are subsidized by the government. So farmers think there is no point being cautious. Just put as much fertilizer as you can to increase your chances of having a higher crop yield. But you pay a price in terms of climate change, but also soil quality, soil health degradation. We can also implement solutions in the broader food system by reducing the demand for food products and agriculture. Addressing food waste and our dietary choices can be very important here, but you have to be cautious because dietary choices interventions can be tricky. There are cultural, personal taste requirements and so on, but reducing food waste should be a no regret decision that everybody can follow, right? So reducing food waste, as we said, 6% of the total emissions are sometimes argued to be coming from waste, and even poor and developing countries waste massive amount of food. So roughly 30% of land, water, chemicals, and greenhouse gas emissions associated with food production isn't necessary. So eating more plant-rich diets. Meat has higher carbon footprint, but you have to remember that you can be a vegetarian and doing a lot of crazy things, and you can be eating meat, but you can be riding a bicycle. So you have to worry about the overall portfolio of carbon footprints for each person. We can intensify agriculture basically to increase the productivity of crops and pastures on the farmland we already have. And there are many ways this is possible. I have already talked about this in drawdown in the land use section and the agriculture section. So we can look at some details here. Reducing emissions from ruminant livestock. So you can look at the numbers here estimated for 2050, but if you look at potential impact of enteric fermentation reduction solutions in gigaton CO2 equivalent per year by 2030, so that's including non-CO2 greenhouse gases, which is important because it's methane that we are worried about. So emissions from enteric fermentation in 2017 was here at just over 2 gigatons CO2 equivalent per year. Projected emissions are expected to be much higher at almost 3.5 gigatons CO2 equivalent, but improved feed digestibility by 2 studied, 3 studies, improved livestock management by 2 studies, and use of feed additives like seaweeds are all able to reduce the CO2 equivalent emissions from enteric fermentation. Improved feed digestibility, then high quality feeds like grains produce less methane in the ruminant's digestive system. Feed additives like seaweeds reduce the production of methane by ruminant digestive microbes. Okay, so those also include seaweed oils, biochar, saponins, probiotics, and methanotrophic microbes that can just respire or eat up methane and produce some other product, of course, hopefully not something worse. But even if it's converted to CO2 is 25 times less global warming potential as compared to CO2 is 1, methane is about 25. Breeding and management, improved forage quality, tree fodder. So there are many ways to do this, grazing management and silvopasture and so on, that we'll look at in a minute. Reducing emissions from manure. So emissions from 2017 were again here at about 1.2 gigaton CO2 equivalent per year. Projected emissions are expected to jump to 2 gigaton CO2 equivalent per year from manure, but reduced N2O from manure on pasture. There are manure management papers arguing for this. Methane biodigesters, kind of composting pits to produce energy. Improved timing of manure application on crop fields. It depends on how badly they degrade and when you put it. So it's like irrigation. You want to do it in the evening to reduce evaporative losses, right? So manure on pastures, manure on crop fields, manure management, all these are solutions. I'm not reading the text in detail. You have to go and read those, but I'm just showing some key figures, and they indicate the pathways and the research that is going on managing manure and reducing emissions like N2O from manure management or mismanagement. Reducing emissions from fertilizers, so potential impact of reduced synthetic fertilizer emissions. Emissions in 2017 were about 0.7 gigaton CO2 equivalent per year, projected to rise from 2017 to 2020 is almost double at 1.2, but this number has to be checked where we ended up by 2020. And cropland nutrient management, drawdown argues for this. Cropland nutrient management by another study by Rowe, cropland nutrient management by Griscom, who wrote about nature-based solutions. And improved synthetic fertilizer production itself can also cut the emissions from fertilizers. Okay, so nutrient management for synthetic fertilizers, compost and manure as nitrogen sources instead of synthetic fertilizers, which are chemically intensive, and also production, transportation, etc. Add emissions as well, whereas compost and manure can be more local. Nitrogen fixing plants as nitrogen sources, so that's been tried and advocated heavily. And herbaceous legumes like clovers are sown in pastures both for their protein as fodder and for their fertilizing effect, nitrogen fixing. Crop livestock integration, so integrating livestock with crops is a traditional practice still widespread in some parts of the world. Once you start going after focused efforts to increase crop yields, then you begin to make concentrated crop patterns rather than mixing with livestock. But if you can show that actually mixing crop livestock integration can enhance crop yields as well as maintain soil quality and reduce emissions, then it's a win-win-win-win. Okay, a detailed review of reducing emissions from rice cultivation. So emissions from rice cultivation rice production in 2017 were 0.51 gigaton CO2 equivalent per year. It's projected to rise to 0.9 by 2050. Improved rice production from drawdown shows some savings. SRI drawdown here. Also, and this is the rice. This is the smart rice something. So this is where you don't put the seeds and flood the land to kill weeds, but you grow the seedling of rice somewhere and you transplant it after a few weeks, which reduces the flooding needs and weed problems and so on. Okay, so I have this acronym somewhere, but I am right now forgetting what it stands for, but you can look it up. Improved rice cultivation. Improved rice cultivation. Rowe argues a much bigger gain in terms of savings in gigaton CO2 equivalent per year. But rice cultivation is a major target for reducing emissions. You have low methane rice. Here it is. System of rice intensification. That's SRI. What does it do? SRI is a rice production system that began in Madagascar. It's also called Madagascar rice in the 1980s and has spread rapidly. SRI focuses on several elements: planting individual seedlings, more widely spaced intermittent watering instead of continuous flooding, compost application, and the use of a rotary hoe to control weeds rather than relying on flooding and drowning out the weeds. So here is an image showing some of that and the spacing, and the seedlings are transplanted from a pot into the field to reduce emissions. One more, reducing emissions from other agricultural activities. That's the total emissions. So potential impact of other emissions reduction solutions. So this is reduction of other agricultural sources in terms of gigaton CO2 equivalent per year. They are projected to rise, and improved savanna burning, fire management, restoration and re-wetting of peatlands, peatland protection and re-wetting can all add to reducing emissions from other agricultural activities. So savanna burning, cultivation of peat and other organic soils. How long is this one? Maybe we can leave this here. It's almost 12 minutes, so let's leave this here and come back and see how much longer it'll take. I have still quite a number of slides left, so it will probably take a couple more podcasts. That's okay, but you can see that I'm being very brief, making the most salient points as determined by me completely subjectively. So as always, go back to the original report, which is available online, to read the details and look at all the excellent references that are provided if you are interested in the details. Okay,